All right. Um, I'm gonna just start going through this, and the first time through, like I'll explain everything I do and try and answer any questions. Let me get through it first, and then we can ask separate questions. I can always pull up the list of proofs that I gave you guys 2 weeks ago, and I can always bring up the textbook and all that, and we can go over problems like that. Um, but for now, I'm just gonna go one all the way through, which shouldn't take too long, at least until the proofs. So, question one, write the next term of the following sequence. This is using inductive reasoning, so we're finding a pattern of it, and then we're giving the next term or two or three. I will say that on the test, I'm probably not going to do just the next term. It might be like the next three terms. So the pattern here, -5 to -3 to -1 to 1 to 3 to 5. We're just adding to each side, two to each term. So our next term would be 5 plus 2, which is just 7. Next, prove the following is false by giving a counterexample. If the product of two numbers is even, then the two numbers must both be even. So product of two numbers, if these are both even, sorry, if the product is even, then these two numbers must both be even. We could just do 2 times 15 is equal to 30. 2 is even, 15 is not even, but our product is even. So this is a counterexample. Question number 3. From question number 2, state and label the converse, the inverse, and the contrapositive. Then evaluate whether or not each statement is true or false. So if our original statement is if the product of two numbers is even, then the two numbers must both be even. The converse of that, and I'm going to write the rules of converse, inverse, and contrapositive. Converse, if our original is if A, then B. Our converse is B, then A. Inverse is not A, then not B. And our contrapositive is not B, then not A. So the converse of this would be if two numbers are even, then their product is even. And this is the converse. Danny, it'll be about the same as this. In terms of truth, if two numbers are even, then their product is even. This is always true. The inverse of this says if the product of two numbers is not even, then the two numbers must both not be even. This is true. And then the contrapositive, which I will put over here to save room, says if two numbers are not even, then their product is not even. And this is false. A good way to evaluate whether or not the truth of a contrapositive statement is true. On number 2, the original statement, this is not true, so the contrapositive must also not be true. Then if those aren't true, then the middle terms probably are true. Question number 4 from question number 2, will there be a biconditional statement? If there is, write it out. If there's not, state why there's not a biconditional statement. There is not a biconditional statement for this because the original and the converse are not both true. A biconditional statement happens when both the original statement and the converse are true. So let's give me 1 second to think about one. So for example, if two lines are parallel, I will get to number 6 here in a minute. For now, an example of biconditional statement. If two lines are parallel, then they don't intersect. So if this is the original statement, the converse is if two lines don't intersect, then they are parallel. Now, I know we haven't gone over definitions of parallel yet, but this original statement, this is true. And if two lines don't intersect, then they are parallel. This is also true, at least in our geometry. Because both of these are true, we can rewrite this as a biconditional statement, which says two lines are parallel if and only if they do not intersect. So in number 4, because both the original and the converse are not true, there is no biconditional statement for it. In the example in blue to the right, both the original and the converse are true, so there is a biconditional statement. Number 5, write the statement that follows from the pair of statements given. If you slept well last night, you will be well rested. If you are well rested, then you will have a good day. So this is really asking you for the law of syllogisms, which says that if you have if A, then B, and if B, then C, you can condense this into if A, then C. So number 5, if you slept well last night, that's your A. You will be well rested, that's your B. Then you will have a good day is your C. So we can rewrite this as if you slept well last night, then you will have a good day. So because these middle terms are the same, they kind of cancel each other out, and you're just left with what's on the outside. Number 6, determine the conclusion to the following statement, given that the hypothesis is false. So this is using the law of detachment, and what that says is if you have a true hypothesis of a true statement, then your conclusion will also be true. If you have a false hypothesis of a true statement, then your conclusion will be false. So what this does is it basically just isolates the hypothesis and then has you determine what will happen with the conclusion. Okay, so the statement says when it snows outside, you shovel your neighbor's driveway. We're assuming that this conclusion is false. So it is not snowing outside. So if it is not snowing outside, then you are not shoveling your neighbor's driveway. I probably spelled shoveling wrong, but that's all right. Yes, Jacob. All right, truth tables. There will be one on there. We need to know that the V, that means or. The upside down V means and the little squiggly line means not. Okay. We also need to know the order that these start. So both statements always start off as true in the first one. So true, true. For the next one, it's true, false. The next one is false, true. And then the next one is false, false. What this does is it gets every combination. It's not meant necessarily to be something like you memorize, but it's every combination of true, false, given two statements. Okay, so A or B. What this says is that for this to be true, either A or B has to be true. both of them can be true, but at least one of them has to be true. So in this first line, A and B are true, so this is definitely true. The second line, A is true, B is false. One of them is true, so this statement is true. Same for down below. And then on the last one, both are false, so not one of them is true, which means this statement is false. The third column, or the fourth column, we're just reversing this column. So because A or B is true, this is false. Again, because A or B is true, this is false, false. And in this last row, because A or B is false, this is true. And then in this last column, we're looking at this column and the A column. So both of those things has to be true for this statement to be true. In this first row, A or B is false, not A or B is false, and A is true. Because both of them are not true, this statement is false. Same reason in the second column. Same reason in the third column, or the third row. And then same in the last row. So all of these are false, because both would have to be true to make a true statement. Okay, the next couple are really just asking you to do algebra and then give reasons behind every step that you take. So in number 8, I'm just going to make step 1 what the actual problem says. I'll say this is given. Then we can combine like terms. So this 6 minus 2. Or simplify, that's fine. And I only want 2 columns. I know in the homework I asked for 3. That was just so you guys could see the reasoning behind it. So once we get here, then we have to subtract 4 from both sides. And we can do this because of the subtraction property of equality, which I'm okay with you just saying subtraction. Then we can simplify. Then we can divide 4 on both sides. And we can do that because of the division property of equality. Again, you can just write division. Number 9, again, first step is always just what's given. I'm going to distribute this 8. So 144 is equal to negative 24b plus 24. And that's the distributive property. Then I'm going to subtract 24 from both sides. When we do that, we get 120 is equal to negative 24b. So we can subtract because of subtraction. And then we simplified. we can divide negative 24 from both sides. We can do that because of division. And then when we divide 120 by 24, we get negative 5. You can. It might help you more than me. It's up to you, really. It's more of an organization thing than anything. It also helps me so you can point to, like, step 3, you did it wrong. It's up to you. And then we need to do a similar thing for number 10. So the first thing I'm going to do is rewrite what's given. Then I'm going to distribute the 7 on the right-hand side. And we can do that because of the distributive property. I'm going to get the r's on the left. So I'm going to add 7r to both sides. We can do that because of addition. Then we can simplify. Then we can add 37 to both sides. Then we can divide by 2. Okay. I know that probably most people have questions just on proofs, which is understandable. Before we get to proofs, are there any questions from 1 to 10? I'll give a minute to think, but we'll focus on that right now, and then we'll dive into proofs here in a second. Okay. Law of detachment. Law of detachment is just taking the hypothesis by itself and then based off of whether that is true or false, determining what the conclusion will be. Okay, so in this example that I have written here, if today is Tuesday, then tomorrow is Wednesday. So right now we're just looking at the hypothesis, and I'm giving you that today is Sunday. Sunday is not Tuesday, so tomorrow is not Wednesday. Okay, if I said that, well, we'll say, okay, so tomorrow, so if today is Sunday, then tomorrow is not Wednesday. Okay, if I give you that today is Tuesday, that means that the hypothesis is true. So if the hypothesis is true, then the conclusion is true. So because today is Tuesday, tomorrow is Wednesday. Okay, so the law of detachment is just about the hypothesis and whether or not that's true, and then what conclusion you can draw from that. Three and four. So 3 and 4 is asking about the converse, inverse, and biconditional statement and contrapositive. So if the original statement is if the product of two numbers is even, then the two numbers must both be even. We determined that that's false. The converse of that statement is just switching the hypothesis and the conclusion. So our statement would be if two numbers are even, then their product is even. Which that's true. The inverse is the negation of the hypothesis and the conclusion. So if the product of two numbers is not even, then the two numbers must both not be even. And again, that's true. The contrapositive is basically just the inverse of the converse. So you're negating the conclusion, that's becoming your hypothesis, and you're negating the hypothesis, and that's becoming your conclusion. So our statement would be, if two numbers aren't even, then their product is not even. And that is false. Number 4 says, will there be a biconditional statement? And biconditional statements only happen when the conditional statement is true and the converse is true. Because our original statement is not true and our converse is true, then we do not have a biconditional statement. They both have to be true for that to be the case. And I gave an example of something that would give a biconditional statement. If two lines are parallel, then they don't intersect, which is true. The converse of that is if two lines don't intersect, then they are not parallel, or then they are parallel. Because both of those things are true, you can rewrite them as a biconditional statement, which looks like two lines are parallel if and only if they do not intersect. Yes, but your reasoning only has to do with the converse and the original conditional statement. So if you know the original statement is true and you know the converse is false, then there's no biconditional statement. If both are true, then there is. And I probably won't give you something as, I guess, convoluted as number 2. I'll make it maybe a little bit obvious, more obvious that the converse and inverse are true or the original is true. So if you give a counterexample, then that statement is false. So on number 2, again, if the product of two numbers is even, then the two numbers must both be even. We found a counterexample. So our original statement is false. So we did false on the original, false on the contrapositive, which makes sense because those are saying the same thing. And then the converse and inverse are both true. But the original statement and a converse are not true. Are both not true. Therefore, there's no biconditional. You can, but you'll have to determine if the converse is actually false. Which again, it should probably be a little bit more obvious than in number 2. This is meant to be more basic than mathy, but that's all right. Okay, before we go to the proofs, any other questions? Yes, the conditional is the original. Okay. This is number 11. When we want to prove that angle 1 is congruent to angle 4, given that angle 3 is congruent to angle 2. So this is one of the simpler proofs if you know about vertical angles. So the first thing we do is, because angle 1 and angle 3 are vertical angles, we know that they are equal to one another. So angle 1 is congruent to angle 3. We also know that angle 2 is congruent to angle 4 for the same reason. And really, I guess this would be step 2. step 1 would be just restating what's given. Step 2, we can substitute one of these things for one another. So because we know that angle 3 is congruent to angle 2, we can replace them anywhere. Okay. So we can set angle 1 is congruent to angle 2 by the transitive property. So just as a side note, I'm going to do this in a different color so you know it's not actually part of it. And yes, you have to give your reasoning. Angle 1 equal to angle 3. Angle 3 equal to angle 1. Oh, sorry, angle 2. Therefore, angle 1 equal to angle 2. Alright, we can also say that, and actually we don't need to say anything else. Because angle 1 is also equal to angle 2, we can rewrite this step as angle 1 congruent to angle 4. And that would just be substitution. And this is what we're trying to prove. So we finished it. You should know all the properties, all the postulates, and the definitions. It's like the first 8 are super important, and the next 4 you use less often, but you can still use them. Those theories we went over last class we had, so the last actual class that wasn't review, those are there to save you steps. The postulates, yes, they're for proofs, but so are the theorems and so are the definitions. So questions on number 11. No, we're not. No, we cannot use notes. We should know the postulates, we should know the theorems, and we should be able to reason down to the proof. Okay. The proof part, I don't know exactly the weight of the proofs yet. It will be significant though. It won't be half the test, but it probably will be a little bit bigger than a fourth. Yeah, the last in white was on number 11. In red, this is number 12. This is the last proof. Alright. So, we are trying to prove that angle HGF is congruent to JFG, given that EGF is congruent to EFG, and EGH is congruent to EFJ. One of the most important things about this proof is being able to keep yourself organized and just identify the angles. When you can identify the angles and do a little bit of math and logic, this proof is decently reasonable. Okay. Step one is always to restate what's given. Actually, I can just do this. And then we need to start using what's given and the diagram in order to get to what we're trying to prove. Okay, so we're trying to find a small angle, but we can find the sum of the bigger angles. All right, so EGF, the angle, this angle right here that I have labeled in white, this is the sum of EGH plus HGF. And we can do this because of angle addition postulate. And we also can get a formula for EFG, angle in blue. That is the sum of EFJ plus JFG. And that's the same reason as the one in white. Now, we have two formulas that we know are equal to one another because of this statement right here. Okay, EGF is the left-hand side, which is all of this. EFG is the right-hand side, which is all of this. So we can set them equal to one another. So we can set angle EGH plus HGF equal to EFJ plus JFG. And that's just substitution. Now we can use our second set for the given, our second given thing, right? And that is that EGH is equal to EFJ. So I'm going to choose to substitute. So wherever I see EGH, I'm going to substitute with EFJ. All right, so I see it right here, so I'm going to replace it. And again, that's just substitution. And then we can subtract EFJ from both sides. And I guess the measure of EFJ. That's okay. When we do that, those cancel. So we're left with angle HGF is congruent to angle JFG, which is exactly what we're trying to prove. And the reason we can simplify it like that is because of, it's really the angle addition postulate, but we can call it subtraction for now, because we're just subtracting some measure. And then that's it. The thing is, the postulate should be common sense by now. Like, angle addition postulate is you can add measures of angles. That should be common sense. You should know that this big white angle we can split up into this small angle plus this other small angle. And those two together are going to be the big white angle. Right? Like, subtraction. I like that postulate. That should be common sense. Same with substitution, really, because you've been substituting things since 6th, 7th, 8th grade. What's different about this is that we're using angles and measurements. Okay, so you guys can all do this algebra very easily. But as soon as we start putting it to geometric figures, it gets a little bit harder. But that's what we're trying to practice. So that is the entire test. Are there any other questions? And I guess before we get there, Austin, yes, part of the skill set we're trying to teach, though, I'm trying to teach, is being able to recognize different angles. Again, a lot of this is just staying very organized. So you need to be able to know which angles are which. That's why actually drawing this and marking it up, it helps. Nah, I'm good. That's what I'm trying to teach. You're welcome. I'll be open for questions. We don't have to end it here, but if there are no other questions, then we can. Jonah, this, like, you can rewind and do whatever you want with it. this will be up forever. In fact, I think as soon as this ends, it should just be up. Yes, I can do another proof. Before I do that, where are you confused on number 12? On what step? Be really specific so I can go directly to it. Okay. Step number 2. I'm going to clean this up just a little bit so I can mark it up again. Okay, step number 2. I want the equations of the big angles. So we're given that EGF, this angle in white, is equal to EFJ, which is, it'll be this angle in blue. Okay, we are given one of those counterparts, so we're given one of those smaller angles inside. We can split up each of those angles into, so for EGF we can split it up into EGH, which is this in green, and HGF, which will be this in pink. Okay, so EGF is green plus pink. That's all that step is saying. And it does the same for EFG. Step number 3 is rewriting this. It's rewriting that EGF is equal to EFG, but it's using the sum of its smaller angles. So we have EGF, which again, it's right here. It's the sum of these two angles. And then EFG is the sum of these two angles. So we're just setting those two things equal to each other like this says that we can. And then step 4 is substituting, and then we have something that we can work with. That's hard to do with angles, especially when there are overlapping angles, and it can be hard to do with segments if there are overlapping segments. You can try. It's not a bad idea. You just have to be very, very careful. And Jonah, I imagine that the difficulty will be somewhere between the difficulty of number 12 and number 11. I think 11 is a little bit too easy, and 12 is probably about as hard as I would go. Like I think that's the ceiling, especially since you guys are so new to this. So let me find another proof real quick, and then I'll put it up. Give me like 2 seconds. Okay. We'll do this again. This might be maybe a little bit too hard, but it's using things that we just went over. So given statement, just repeating everything that's given. So angle A is complementary to angle ADB. So this angle A is complementary to angle ADB. So those two added together are 90. Angle C is complementary to CDB. So this angle, those two added together are 90. And angle DB, or sorry, line segment DB, splits this angle in half. Alright, so we're just using everything that's given. And we're trying to prove that angle A is equal to angle C. So we know that angle A plus angle ADB is equal to 90. And we know that angle C plus angle CDB is also equal to 90. That's just a definition of complementary. Because of this statement, we know that ADB is equal to CDB. And that's the definition of bisect. It splits it directly in half. So now, we can do a little bit of substitution. You could actually use a theorem and just be done with it here. But we'll do it in the way that I think you guys would. We can substitute ADB. But first, we can actually set all of this equal to one another. That's substitution. And then we can substitute again using this substitution. And we can just pick one. So I'm going to pick substituting CDB for anywhere I see ADB. Yes. So now we have two things on the same side. Those cancel each other out. So you're left with angle A is equal to angle C. No. No, you cannot. This is angle ADB, and this is angle CDB. It's not... Those aren't multiplying. Nope. Can't do that. Because you don't know that those two angles are equal. Part of this proof is establishing that they are, but you can't just assume it. A DB is not like, it's not like multiplication where they just kind of cancel each other out. That is an angle, and it requires the entire angle. Now I think what Austin was saying earlier, I'm going to make this small real quick so you can see it all. So what Austin was saying earlier is, I think, is you could just name all these angles. So you could name this angle 1, this angle 2, this angle 3, and this angle 4. And then maybe the bigger angle, angle 5. You can do that. It's just sometimes that's harder to keep track of. The triangle doesn't prove anything. That could be drawn not to scale. Because you can't assume anything that's not explicitly given on the diagram. Everything else you have to prove directly, which is exactly what we just did. And again, if you have an angle, like in step 3, ADB equal to CDB, you're really talking about measures here. You're talking about a measure of some angle equal to the measure of some other angle. You can't get rid of dB in either of these. That's not how it works. dB is a segment. Okay. I'll leave this open for the next like 5 or so minutes for any like last minute questions. Um, I'll try and be as available as I can at like 8. But that seems like a pretty comprehensive review. So the thing with protractors is that sometimes there's human error. So you could, but you're assuming that a lot of things are perfect. Why is step 4 substitution? Because we know I see. Because of step 2. So we know that A plus ADB is 90. We also know that C plus CDB is 90. So it's really not substitution, it's more like transitive property. But substitution is really just, or transitive property is really just a special kind of substitution. So we set A plus ADB equal to 90, C plus CDB equal to 90. Because they're both equal to 90, they're also equal to one another. Ethan, does that make sense? You can. You're always welcome to ask questions. What I don't want to do is reteach entire lessons. So I can clarify stuff, and I can say you did some stuff right. Uh, but am I gonna make sure you know all the postulates? Probably not. What I would do tonight is like maybe after looking over this practice test one more time, like just go to bed. That's the best thing that you can do. The last thing I would want is for you to stay up all night studying this stuff and then come in tomorrow morning with clouded head. Okay. You're welcome. Thank you guys for listening. Um, email me. Try and get me in the morning. Try and get me during activity period. Uh, this is pretty comprehensive. I get that proofs are new. Um, I'm not expecting you to be perfect on it yet though. So don't panic if you get one or two steps wrong. That's okay. I want you to get them right, but that's we'll be doing these all year. You will have no homework. So yes, you can study for the test. All right. So I will end it now. Again, thank you. This should be up as soon as I hit stop streaming. Um, so yeah. Good night.